So welcome back. So today we are going to discuss independence. So the definition is that we say that two events A and B are independent, which I will denote by this symbol, if the probability of A intersection B, probability of A and B, is equal to the probability of A times the probability of B. Okay? So there is a so let's make an example. Imagine that we have two dice. We roll these two dice, and so the sample space is composed of elements which are the numbers which are shown on the up face of the two dice, where these D1 and D2 go from 1 to up to 6, and each of these outcomes is equally likely. Okay, so the probability of any omega is equal to 1 over omega, which in this case is 1 over 36. Okay, so for example, you can consider two events, A, which is D1, which is equal to 6, and B, which is D1, D2, which is equal 1. Okay, so now it is clear that these two events are independent because because essentially this sample space can be represented as a direct product of the two subspace. So these concern the first dice, and the second concern the second. And it is clear that the probability is the product of the two probabilities. So it's the probability that D1, so this, you can write it as probability of D1 times the probability of D2. Okay, and each of these two probabilities is equal to 1/6 for every outcome of the two dice. So it is clear that also if you do the calculation that these two events are independent, and the probability of this event is just 1 over 36, because this corresponds to D1 being equal to 6 and D2 being equal to 1. Okay, but what about more complex situations? So when, for example, we consider the event C, which is D1 plus D2, which is equal to 7. Okay, so now it is not exactly clear whether, for example, event A and C are independent. So in order to check whether they are independent or not, one has to do the calculation. Okay, so let us compute what is the probability of A intersection C, and the probability of this event, if D1 is equal to 6, then D2 must be equal to 1. So it's 1 over 36. So the probability of A, we already said, is equal to 1/6. So we have to compute the probability of C. And what is the probability of C? Is 1 is the number of favorable events for C divided by 36, which is the size of omega. And how many possible outcomes contribute to C? Well, when D1 is equal to 1, then D2 must be equal to 6. If it is equal to 2, then D2 must be equal to 5. And if D1 is equal to 3, this must be equal to 4. And the opposite, okay? So this times 2. Okay, so there are 6 possible cases in which the event C occurs. So this is 6 divided by 36. So this is 1/6. So what we conclude then is that events A and C are independent. Okay, now if you compute, if you instead look at the event D, where D1 plus D2 is equal to 8, you can do the same calculation, and you can do it as an exercise, and you can see that A is not independent of D. So these two events are dependent. Okay? So the lesson of this simple exercise is that sometimes independence is intuitively obvious, sometimes it is not, and so one has to do the explicit calculation. Okay, so in order to understand what independence means, it is better to introduce another concept, which is the one of conditional probability. So the definition is that the probability of A conditional to B is the probability that A and B occur divided by the probability of B. Okay? So notice that so this is the definition. So if A and B are independent, then this probability is the product of the probability of A times the probability of B. The probability of B cancels, and this is equal to the probability of A. So now you see an intuitive understanding of what does independence mean. It tells you that whether event B occurs or not does not give you any information on whether A occurs or not. Okay? So in some sense this means exactly that the occurrence of event A is independent of the occurrence of event B. Okay, so the other information that you get from this is that if we are in classical probability, then this will be the number of favorable events for AB, and this will be the number of favorable events for B only. So you see that the total number of events cancel, and this is just the number of favorable events for A and B divided by B. So you see that in computing this probability, we are essentially replacing, with respect to this one, we are replacing omega by B. Okay? So indeed, as I told you, we should always write probabilities as conditional probabilities. So when you condition on an event, is like having more information on the conditions under which you are interested in computing the probability. And so it's like changing omega into B. Okay? Okay, so now all of this, I would like to tell you how all of this generalizes to more than one event. Let me keep this example. So now imagine that we have a sequence of events. A sequence of events A1, A2, AN. Okay? Then we can compute the probability of A1, A2, etc., AN by using just the relation that we have derived so far, so that the probability of A and B is the probability of A given B times the probability of B. And so you can write this as the probability of AN conditional on all the other events times the probability of AN minus 1 conditional on all the remaining events times the probability of the second event given A1 times P of A1. Okay? So, now of course, this equation, you can also write it as probability of B given A times the probability of A. And likewise, you can expand this expression in any possible order between these n events. Okay? So now you can say that we can define what does it mean for these events to be mutually independent. So A1, AN are mutually independent if for any choice of a subset of the integers 1 to n, we have the probability of the union of the events in this subset is equal to the product of the events in this, of the probabilities of the events in this subset. Okay, so alternatively, you can also say the same thing by saying that if these events are mutually independent, then the occurrence of any subset of these events does not give you any information on the likelihood that another event will occur. Okay? So that for any subset, the probability that an event, say AI, occurs, given, this is the intersection, given that a certain number of events, of other events, occur is equal to the probability of event AI. Okay, so this is precisely stating that, and in this case, I should add that I should not belong to I. Okay, so this exactly means the fact that the occurrence of these events does not tell you anything on the likelihood that event AI will occur. Okay, and this is true for any I. Okay, so this notion of independence, so there are a couple of things that I want to remind you about independence. First of all, that independence is a notion which is much stronger than pairwise independence. Okay, so you can say that pairwise independence you can say that a set of events is pairwise independent if the probability for any choice of two events I and j is equal to the probability of AI times the probability of aj for any choice I of I and j. Okay, so the fact that, of course, if the events are mutually independent, then they are also pairwise independent, because there is a subset which is composed of pairs for which, so this definition here is contained into that. But the converse is not true. Okay, pairwise independence does not imply mutual independence. And as an example, you can just take these three events here. And as we have shown, A is independent of B, A is independent of C, and by symmetry, or you can just do the calculation, and you will find out that also B is independent of C. However, A, B, and C are not independent, because if A and B occur, then C occurs with probability 1. Okay? So the probability of C given A and B is equal to 1, which is different from the probability of C, which is 1/6. Okay, so pairwise independence is not independence. Okay? Okay, so there are two other general rules that I would like to remind you, that I'm sure you have already seen. So, and one is the total probability rule. Okay, in order to discuss the total probability rule, we need to introduce a set of events, say C1, Cn, that we can consider as a complete set of causes. So by this we mean that the union of all these events is equal to omega, which means that at least one of these events will occur, and also that Ci intersection Cj is the empty set. Okay, so this means that at least one of these events occur, and this means that only one of these events will occur. Okay, so then for any event A, you can write the probability of A as the sum of the probability of A intersection Ci. So this is just using the additivity rule, because essentially if this is my sample space, this is the event A, and the set of causes is like a partition of the sample space in different events Ci, which are mutually exclusive. Okay, so because they are mutually exclusive, then also the you can write that A is equal to the union of A intersection Ci, and A intersection Ci intersection of A intersection Cj is equal to the empty set, because Ci and Cj have no intersection. Okay, so so then, because of these two things, you can write you can expand the probability in this way, and then you can use the definition of conditional probability and write this as the probability of A given Ci times the probability of Ci. Okay, so why is this useful? Because this tells you that if you want to compute the probability of an event, it is often more practical to find a complete set of causes for which you can compute the probability of these causes, and for which you can compute more easily the probability of the event A given one of these causes. Okay? Okay, so the second rule I want to remind you is Bayes' theorem. So Bayes' theorem is also a very easy statement, and essentially has to do with computing from the probability of an event A given the cause Ci, what is the probability of the cause Ci given the event A? Okay, and the derivation is very simple. If you want to compute probability of Ci given A, given A, then this is just the probability of A and Ci divided by the probability of A. But now I can write the probability of A and Ci as the probability of A given Ci times the probability of Ci, and the probability of A, I can write it using the total probability rule. Okay, so this statement is called the Bayes theorem. Okay? And so you see that you can compute the probability of causes given a certain event in terms of the probability of the event given the causes. Okay, and this is the basis of statistical inference. So because you can think of, so in statistical inference you call this, you can think of A as being a certain event you are interested in, and C being a certain model that describes this event. Okay, but you may have different models. Okay, so this what is so what is here is what is called the likelihood. It tells you how likely is the event A under cause Ci or under model Ci. This is instead the prior probability, which is the probability that you have on model Ci or on cause Ci before you observe the event A. And this, all of this is called the evidence, and it's the probability of A. Okay, and this part here is called the posterior probability. Okay, and tells you after, so you have a prior assessment of what is the probability of Ci, then you observe the data, or you observe the occurrence of an event A, and this modifies your likelihood, your probability about Ci, because you have observed A. Okay, so in general you see that so A here represents, if you want, the data, the observation, and C represents the theory. So what you can compute from your theory is what is the likelihood that something happens. But what we are really interested in is what is the likelihood that your theory is correct given what you have observed. Okay? And this is what Bayes' rule allows you to compute.